So we've spent the last week, some of us, talking about or trying to figure out rather this theorem. And this theorem has been called the Pythagorean theorem. And some of you guys knew that, some of you guys didn't, but that's okay because by yesterday, hopefully, you guys would have figured out what this theorem was talking about and how you use it to your benefit when you're dealing with right triangles. So I just want to go over what it is that you guys did and then help you use that to transition to the next step of using this theorem as opposed to just drawing shapes to figure out answers that way. So if we think about this first example, right? Yesterday you guys had on the paper that this was a side length of 6. This was a side length of 8, and we didn't know what this side length was yet. I mean, you could measure it, but you just didn't know yet. Now, they told you that what you were supposed to do was find the whole area of this space. So if we know that the side length is 6 and we can make a square, then the area of this whole square should just be 36 units, squares, whatever it is, centimeters, we said, squares. All right? And when you did the same thing for this 8, I'm so sorry that it's the wrong size. We did the same thing for the 8. You found out that 8 times 8, right, if we're making that square, is the 48 centimeters squared. When we measured that red side, we were able to figure out that, okay, it's not just that we know what 6 is and we know what 8 is. We also can measure this side length and find out that this side length is actually just 10. Ooh. And now that we know that it's 10, we can do the same thing. If we take that area and we look at what it encompasses, right, all of this space, we figure out that the area of this side length is actually just going to be 100 centimeters squared. Now, one of the things that you guys struggled with a little bit, which was amusing this entire week, was just noticing what actually is happening with all of these numbers. So if we look, right, we have the number 36, we have the number 64, and when you add them together, you actually get that number 100. So what's happening is that if you take the area of these two smaller squares and put them together, you actually get the area of this bigger square, which was what the goal was, which is what I wanted you guys to be able to figure out. So you saw that example, and your goal was to be able to translate it into the next example that you were given, which we'll look at right now. All right, so in this next example, you guys were given the side length of 2.5, the side length of 6, and again, you didn't know what that hypotenuse was, but by the time that you measured it out, you knew that it was 6.5 centimeters. All right? So same thing. We're trying to figure out the area. We're trying to figure out what's going on. So if we look at the area of this square right here, we knew that it was going to be 6 25 centimeters squared. If we looked at the area of this square, of this side length of 6, we knew that the area was just going to be 36. And then when we looked at this side length here, when we finally measured up this side, the area of it rather, we knew that it was just going to be an area of 42 25 centimeters squared. All right, so if you weren't able to notice it in that last example, maybe you noticed it here, that the area of these two smaller squares, right, 36 and 6 25 actually totaled up to be, if you need those zeros there, 42 25. Perfect. So again, we have this example where the two smaller squares are totaling up to be the bigger square. So your next step in that discovery was to be able to figure out a rule. What rule could you apply? And a lot of you guys wrote down, well, the two smaller squares equal the bigger square, but the objective is to be able to write it as an equation. That rule needs to be something that you can generalize and use for whatever situation you find yourself in. So now we find ourselves in the precarious position of trying to make something that makes sense and that anybody can use as long as they need to find the missing side length of a square. So let's generalize it now. You have a rectangle. Wow. You have a triangle, and you know 3 of its side lengths. Realistically, you don't, but if you assign them a variable, you do. All right. We know that if we want to find the area of the bigger square, that we have to square this other side length, right? We have to find the area of this square because the areas of this square add up to the bigger square, not just the side lengths, right? So we know that A, in order to find the square of A, we're going to do A times A, or just A squared. All right, same thing for B. We want to be able to find the area for B. So in order to find that area, in order to find that square, we're going to do B squared. And we didn't know if we had C until we could add A and B together, right? So if we could combine the smaller square with the bigger square, or the 2 legs, I guess I should say, then we would be able to figure out what the area was of this biggest square, right? Because they would be set equal. So at this point, we knew that A squared plus B squared would equal C squared. And that's the general equation or theorem or rule, whatever it is that you want to say, that I wanted you guys to find. So if we can use this now in all situations, then that's really helpful for us. So I just want to show you 2 examples, and then you guys can get started on the assignments that you're doing. So one of the examples that you guys would have seen, or maybe you didn't get to it, but one of the examples that you will see is where it tells you to find the area of one of the squares. So you might be given a situation where you know that the area of this side is 16. You don't necessarily know the side length, but you know that the area is 16. You might be given this other triangle's area, or the side length's area, where you know that the area is going to be 9. You don't know what that side length is, but you do know that the area is 9. We want to be able to figure out, well, what's the area of the bigger square? And in order to find the area of the bigger square, you need to know C squared. So if you can see it right away, you know that you should just add those 2 numbers together because you're just looking for areas, then so be it. But if not, the biggest thing that you can do is plug it into the equation. So we have A squared plus B squared equals C squared, right? These are already the areas. We don't have to do anything because we already know that A squared is 9. We know that B squared already is 16. So we just need to figure out what C squared is. We need to figure out that area of C. 9 plus 16 is 25. So the area of this big square is just 25. Perfect. You might also come across a situation where something else is happening, right? We're still trying to find the area, but maybe they give us different pieces of information. So again, we know that the area of the smaller square might be 25. That's great to know. We can use that later. And maybe it tells us that the area of the biggest square is 169 centimeters squared, right? Now, we're looking for this side right here, side B. Now you might say, okay, well, I just have to add these 2 areas together. But the problem with that is that we've already identified that C is our hypotenuse. C will always be our hypotenuse. It'll always be our biggest side. So we can't just add those 2 numbers together. So if we're not adding, we're probably subtracting. We're doing that inverse, right? But either way, we can still plug it into our equation. A squared plus B squared equals C squared. So you know that the square of A, the area of A, is 25. We don't know what B squared is yet, but we do know that the area of C, our hypotenuse, is 169. So if we subtract 25 from both sides, we find out that B squared equals 144. So the area of this big square is 144. And what's nice about this is that we never have to know the side lengths if they're just asking for the area. However, you'll come across situations where you do have to know the side lengths because you're no longer looking for the area of that side length. You're just looking for the length of the triangle. And that's going to be our goal, and that's what you'll see throughout the remainder of the chapter. Alrighty, so now we're in a situation where we're finding the side length, we're not finding the area. So in order to do that, we have to know at least 2 side lengths that are already there, right? So with A, we know that our side length here is going to be 8. For B, we know that our side length is 15. And we need to be able to figure out what C is. So in order to do that, right? You might say, okay, that's easy. Let me just do 8 plus 15. Oh, that equals 23. So this side length here must be 23. I think that's 23. All right, but that's wrong because we can't just add the side lengths. What we've been talking about are the areas. When we talk about how to find the bigger square, the smaller square, we've been talking about the areas of the things that have been happening. So that's very, very wrong. We're not going to do that. And if you see your friends doing that, poke them in the eye. So we need to step backwards. We're going to use this equation again, right? The square, the area of side length A, plus the area, or the square of side length B, is equal to the area of side length C. All right? So we know that our side length of A is 8, so we're going to square 8. We know that our side length of B is 15, so we're going to square B, and that's going to help us figure out what C squared equals. All right? So 8 squared is 64. B squared, 15 times 15, is 220. Oh, no. Ooh, 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 ooh. B squared, 15 times 15, is 225. And all of that's going to lead us to what C squared equals. All right? So 64 plus 225 is 289. So 289 equals C squared. All right. Now, that's fine and dandy because it gives us the area, but this time, right, we're not looking for the area, we're looking for that side length. So to find the side length, we need to figure out, well, what number times itself equals 289? And you might say, okay, well, let me just divide. But dividing by 2 doesn't give you a number that multiplies by itself. So you have to take actually the square root. All right, so if we want to be able to figure out what C is, we have to take the square root of 289. And this is why I was stressing your perfect squares so early in the school year, because you have to be able to know at least what numbers are close, if anything. So the square root of 289 means that C just equals 17. So our side length of the hypotenuse is going to be 17. So now we know we have 8, 15, 17, that's our triangle, right? If maybe you didn't think of 17 and you just put, oh, okay, that it's going to be 289, you could look at this and know that that's probably not going to make sense. So we're going to stay away from things like that. All right, moving on to that next example. Again, we're trying to find the side length. Find the side length, all right? So you might be given a triangle, and these numbers are absurd, I'm very aware, that has 99 as a side length, and also 101 as a side length. So same situation, we can't just say, oh, okay, well, 101 minus 99, that means that this must equal 2. It doesn't work that way. Or worse, 101 plus 99 equals 200. That would automatically be a lie. You have to make sure that you're using the rule properly. And until you really have practice with this rule, I want you to write it out each time. So as you get through your lesson today, you're writing this out each time. So we have a squared. We don't know what that is yet. But we do know that b is 99. So 99 squared plus a squared equals 101 squared. Awesome. So now we're just doing some math. 99 times 99. Ooh. Gotta zoom in. Is 9,801. 101 times 101 is 10,201. Great, we have all of these sides, but we need to get a squared by itself, right? So in order to do that, we're going to subtract 9,801 from both sides. All right, and we find out that a squared equals 400. So again, we're in a position where we need to say, okay, well, what number times itself is going to equal 400? So in order to do that, we can take the square root. The square root of 400 is just 20. So we know that our side length is going to be 20, and that makes sense because it's our smallest side. If we had put 400, we would know that that's wrong because it's the biggest side, and that doesn't make sense. Or the biggest number for the smallest side, and that doesn't make sense. So we know that the number is 200. A lot of the problems you're going to see today involve triangles, so I'm not going to really, actually just kidding, 1 second. You might be given a situation where they just say, okay, well, A equals 12 and B equals 5. So what does C equal? Again, if it wasn't obvious enough, which is okay, you're just going to plug it into the equation. So A is 12, B is 5, and we don't know what C is. So 144 plus 25 equals C squared, right? 169 equals C squared, but we can't stop right there. We have to find the square root. And we know that the square root of 169 is just 13. Great, so you're given us, oh, kill me. Sorry. You're given a situation where you have the side lengths, they give it to you without the use of a triangle, and you don't need to draw that triangle because you know this equation, you know this theorem now. So your work today, you're going to do all of it. It should only take you like 15 minutes, which is why this video is so long-winded, and you have the rest of the class to do something quietly or independently, whether it be for another class or just for yourself, but you cannot act a fool today. All right, talk to you later, bye. The root of 4...